Oh, okay. Hi, everyone. Nice to see this big crowd. I was going to ask whom of you would self-titulate yourself as working with data, if you have that slightly broader sense than just data scientist. Who would say that? Okay, so even a very much larger bunch. Who of you are a bit familiar with statistics? Because, okay, yeah, okay, that's good. Then I have an idea. These two are cats, aren't they? The pictures are taken from a research article from 2017 about adversarial attacks, if that's a word that you know of. You know where this is heading.
For the next That's what you learn in EIT summer school.
They tried to feed these pictures into Google's, by then, very high-performing image labeler, Inception v3. And the first picture, they say, well, we're quite certain that it's a cat. If we're allowed to round a little bit, they're 100% sure it's a cat. It could be a different type of cat, who knows? But it's definitely a cat. But the other picture, is that really a cat? I think so. But Inception thought it was guacamole. And I think it's a funny example. Do the computer really think that the cat is mashed avocados? Most certainly it doesn't. It doesn't really have ideas about what it is. It only had some training set, some test set, performed quite well. People did not probably use SHAP on it, so they just said that the model performed quite well. And then some other researchers come and find this really stupid example. They probably added some white noise. I have the reference at the end. There's a really good blog post on how to reproduce this if you're interested. And why neural networks are sensitive to adversarial attacks like this? People are not entirely consensus on it, but the way I think about it is like this. If you have a complicated model, it will identify patterns in that data. And the computer will have no idea what is a reasonable pattern or how it should explain things. That is always up to humans, at least this far. And one way to think about causal inference is really about that. We're not happy to just find the statistical patterns in a data set. We're interested in what are the causal structures. And for those of you who are wondering, like, what are these two weird words? Think about it this way. Causal means it has to do with cause and effect. Inference, that means to infer. It means drawing conclusions. So causal inference is drawing conclusions about cause and effect. Or some bad translation to Swedish, for you who speak Swedish, could be like slutledning, maybe. I don't know. It's very convoluted. Who am I? My name is Ludvig Hult. I'm a PhD student at Uppsala University, where I study machine learning and causal inference. We try to find the best of two worlds, where we try to draw these robust conclusions while still using modern machine learning techniques. The first 3 points on the agenda is more about the what is. So I will not give you a definition, actually. I will give you a characterization by example. And, sorry, I need to check the time. OK. And then at the end, I will talk a little bit more on the why. Maybe you know this comic. It's from XKCD. It's a quite common example. Someone takes a statistics class and they learn about correlation and causation, and they know that these are not the same. A statistical pattern is not a causal. But there is another view on the same topic promoted by some people in this field of research. It's a philosophical principle. It says that if I find two things that are statistically dependent, something causes this. They won't be just spontaneously if you don't have small size samples or something. And then that is the reason. So there's always some reason, some causal background. And this is my first characterization of causal inference. It's acknowledging that every time you see pattern, there's a reason for that. And it's not settling with just saying there is a pattern, but actually finding the causal direction. My second characterization is from Miguel Hernan. They use this in the data science education at Harvard. They categorize 3 typical categories of tasks that you do in data science. The first one is answering questions about a description. Let's say you work at a beer company. Someone asks, where do we sell our light lagers? The answer is in the data. Just calculate that, and you will have the answer. The second category of tasks is about prediction. People ask you a question that does not have the answer directly in the data. Maybe they ask about the future. How much beer will we sell in Germany in the spring? It's in the future, you don't know. But the data has seasonal patterns and geographical patterns, and it helps you answer this question. And causal inference is, in this setting, the next step, answering the even more difficult question. What will happen when we start to intervene on the system? If we don't have data on, for example, buying Google ads, this will be a very difficult question. But maybe one of your branches in your organization did try that. They are not comparable to every other part of your organization, so you really need to think a lot before answering the question. Causal inference is not a certain tool. It's answering certain questions, and it's this type of question. We have a certain toolkit, though. And the first, and I think the best place to start, if you don't know anything about causal inference from before, is structural causal models. They are equations of this sort. It might look a little bit scary, but there are several parts that are not that important. The most important things are the things on the right, the x and y's in this case. Those are the variables that we might have data on. We say that they get their value from the thing on the right. It's an equation sign as in an assignment in Python. And it's some function, fx and fy are the name of those. And in one case, it's a function of a random variable ux that we don't know. It will make x random. But y, in this case, is both a function of the random variable uy, but it's also a function of x. We say that x is a direct cause of y in this type of model. We can represent this graphically, and you can see there's a correspondence. There's an arrow from x to y. So x causes y. We can extend it to more variables and introduce something, maybe z. And you can see in the equation that it corresponds to the graphical representation. Z has no arrows coming in. It is only a function of uz. X is a function of ux, but also of z. So there's an arrow from z to x. And y is causally affected by both x and z. We call this diagram the fork. It's one of many different ones that you learn to recognize. The funny thing with this type of model is that you can do what we call interventions. We can set the value of x in this case to something, let's say 9. And for those of you who have read a bit more statistics, the interesting thing is that now the distribution of x, y, and z will not be the conditional distribution that you might find by just subsetting your data to the places where x equals 9. This will give rise to different probability distribution. And this means that it will model interventions, and it will model what will happen when we do something. Putting it in a little bit more context, we start with a structural causal model that models how we intervene on a system. Since that is rule for how you produce random variables, the x, y, and z, it will include a probability distribution on x, y, and z, or like how x, y, and z randomly correlates. And from that, you have data. So the two first steps of data science is answering questions about that probability distribution. What is the shape of my data, essentially? But causal inference is trying to go all the way back to the structural causal model. And this picture also explains why it's very difficult what we're doing. Because there might be several different structural causal models that give rise to the same probability distribution and the same data set. So it's what you in math call an inverse problem. You need a lot of assumptions to make this happen. So this research in causal inference is very much about being transparent about what your assumptions are, for example, drawing them graphically so people understand them, and minimizing the amount of assumptions that you need. Okay, so now you know, now you hopefully will recognize this graphical model and know that it's okay, we use them to explain the causal structure. How do we use them? I will give you an example with what we call adjustment methods and give you an example how to do that in some lines of Python. The case we're interested in is a famous dataset from the 80s about kidney stone surgery. In a subset of that data, we're only comparing open surgery and minimally invasive surgery. And we want to know what is the average causal effect, or the ACE, on the kidney stone, on the success rate of getting rid of the kidney stones. I can produce that in a few very compact lines of Python. I do make the data from a summary table, so it's kind of like cheating. And the data looks like this. I've added a third variable. I will talk a little bit more about that in a while. Every variable is 0 or 1, so they are binary, so I don't have to think about the feature engineering part of this. But for every patient, there's a 0 or 1 whether or not they got the open surgery, if there was a favorable outcome of the surgery, and also whether the kidney stones were large or not. And just looking at the average over the whole data sample, the blue bar is the average outcome for those with open surgery, and the reddish one is the minimally invasive. From this, you can say that, oh, they're quite even performing, but open surgery seems to be a little bit worse. The funny thing happens when I group the data, by the kidney stone size. And now you can see that open surgery is worse for both subgroups. This is a funny statistical thing we call a reversal or Simpsons paradox, where something can be good, or in this case, bad on average, but good for every individual. This is really funny. And the explanation you can find in the structural causal model. The data comes from this fork diagram that I talked about. And comparing with the Reichenbach principle before, the reason that A and B are statistically dependent is also because there is something else affecting both. So we want to know what is the causal effect from open surgery on whether or not the surgery was favorable. But it's confounded by this other variable with large stones. There is rules in structural causal modeling for how we should do the analysis. In this case, we should include this as an extra regressor, for example, or we should reweight our data accordingly. The most interesting thing is that if the data was more complicated, as long as we know the graphical structure, there is a quite simple rule for how to make the right analysis. The gist of it is that the causal influence from the surgery on the outcome must go in arrows that goes from surgery to outcome. But the statistical correlation can be created by any arrows going in any direction as long as it's connecting the treatment and the outcome. The takeaway for you is that as long as we know the graph, it's possible to do the right thing. So we do what we call a backdoor adjustment. We look at the backdoor arrows, those that goes into the treatment choice, and confounded the relationship. So we identify a backdoor adjustment set, and we apply an algorithm. The average causal effect, you see the equation for that on the left, is an expected outcome for two different groups. And we use this do intervention that I said before. So we needed this type of model to explain this. And there's a relatively simple formula as well for computing it, in this case with binary data. The only thing I want to draw your attention to in that equation, the red one, is that you have P of x bar z divided by. So we say that that's an inverse conditional probability. And this estimator is called an inverse probability weighter, or a propensity score weighting estimator. And those are implemented in libraries. This is my point. There's a library that I imported in the previous code snippet. It's Microsoft backed. I feel it's a little bit immature still, but it has all the basics in it. And it's a quite nice API. It's called DoY. You can find it on GitHub. The first thing you need to do is define the graphical structure. Here you do it in GML, which is also compatible with NetworkX for those of you who work with that. So this is the 3-variable fork diagram from before. I input that and my pandas data frame and create this causal model, which is a new object that has both the graphical structure and the data with all its statistical patterns. I ask it to find out how should I adjust my data, what was a confounder, and so on. And then finally I say, please compute the effect via this inverse probability estimator. And it will say that it's a positive effect of treatment A, or the open surgery. And that's consistent with what we saw in the subgroups. It's good for everyone, the causal effect is positive. This is just what we like to see. So that was an example of a toolkit for using this structural causal information in our analysis. There are, I can say, lots of more difficult and involved ways to do this analysis, but this is one of the good starting points. When do we need to concern ourselves with this and not only think about statistical patterns? Should I reach for causal inference if I have a new problem, I've never seen it before, but I have some data? Then I think probably not. You should start thinking about the domain knowledge about this problem, because if you are to reason about graphs and make assumptions, you need that knowledge first. This is maybe not your starting point, but it's the next step. I guess a lot of you work in web, maybe? Maybe? Nod? Maybe? Shake your head? Some people at least. So you might A/B test your site and see how that causally affects your customer behaviors while searching your site. You do an experiment. Can I do that and not think about this weird framework? Well, maybe. It depends on how many customers you have, how many transactions do you run in your experiment, and what will the sample size in your experiment be. If you can do good experiments, then you are quite fine. But if you cannot make perfect experiments, this will help you overcome those problems. If you need to understand not only that it is a causal relationship, but you want to know how that causal relationship is manifest. This is very important, for example, in detecting discrimination in observational data. Then this is the type of framework that you typically use. Or if you simply just have non-randomized data and you still want to draw a conclusion, this is the framework you use. So, a slight bit of outlook, and to give you, this was kind of the basics of what it is and why. Where is it heading? So, the older research, this whole field was started when statistics started, something like 100 years ago. But it has got a big upswing in the last 15 years. So the well-studied part is what I talked about before, like weighting and matching, which was the type of estimator that I showed you. The more recent and current research is about causal discovery, when I have a data set and I don't know that graph. I said that you need to know the graph, but if I don't, what can the data tell me? And this is causal discovery, and it's also a big part of Bayesian network research, if you know something about that. We're also looking at transportation properties. Maybe I have an experiment on this branch of my organization and I want to, so we call it transport those conclusions to some other group. It's kind of a transfer learning setting, so to say. That is quite current research. And what is more the bleeding edge here is this deep marriage between this type of framework and the more standard machine learning methods that you might know of, like neural networks, for example. So some of the big thought leaders in neural networks are turning towards causal inference field as well. So we'll see what will come out of that. In summary, causal inference is about separating the causal patterns in your data from the purely statistical artifacts. And using correct assumptions, such as about the graphical structure, we can draw robust, good conclusions, even if we have data that is not perfect. You don't always need this type of framework. It all depends on your data. If you do have good experimental data that you're very trusting in, it might be fine either way. And by using some of the conclusions from this research field, such as about robustness and invariance, I think that we will see this more and more integrated in our standard methods coming forward. And hopefully the methods will be able to not confuse cats and avocados. So if you thought it was interesting, please find me in the break or send me an email. You can find me on some different platforms. I'm not very active at Medium, but I've written something at least. So thank you for your attention. Do you have any questions? Do we have time for questions?
Yes.
Yes.
Perfect.
Hi, thank you. Can you say something about Rickenback's common cause principle and the history of it, or does it predate the other one? Correlation does not imply causation, or how it arose, etc.?
it's a philosophical statement. Hans Reichenbach was a philosopher in the 50s. So the history of this is that, okay, causality is a philosophically very complicated problem, like what is it even? And people are not agreeing, so I should also say that this is a little bit debated. It doesn't really work well with quantum entanglement. It's one of few exceptions, maybe, depending on how you see it. And his classic example with this was like geysers that fire irregularly but typically in sync. And he said that, okay, this could probably not be chance. There must be something that is the explanation for this. And in his case, it was like geothermal properties. It says that there's something, and this is really from a philosophical standpoint. It might not be something that is simple and something tangible. I think the good way to think about this is, for example, when you have spurious correlation, the thing that is the reason for why you have kind of correlation structures is that you have a low sample. So it might not even be a statistical dependence. And this is the other way to think that it's maybe not a really dichotomy between these two perspectives. I see a statistical dependence between A and B, which is a different thing from a correlation, which I have in this slide. So it's maybe slightly deceiving. Correlation is just a linear interdependencies between two things, whereas statistical dependency, in this, as in this case, is in a very, very general sense. Wasn't it roughly an answer? Perfect.
Hi, really nice talk.
Thank you.
I come from a background in like brain simulation, and there we have very complex graphs, but the graphs are brain networks. So how can you apply this to more complex, not just 3 kind of connected graphs?
So I think that causal discovery is the thing you would typically lean against. Either you do some kind of, you say that you have a certain pattern in your graph that is repeating, or you might say that this type of structure is allowed or disallowed. The problem that you find is that you have a combinatorial problem with how many different graphs you can make. Let's say that you have 1,000 variables, which might be too little in your case. I mean, the number of possible graphs are immense. So one thing that is current research is trying to recast this as a smooth optimization problem. So you can look at if the functional dependencies in the edges in your graph is of a certain kind, like they are generalized linear, then there are like smooth techniques to deal with this. You don't get a uniqueness of the solution to the problem, but that might be fine. I mean, this is something that we see, for example, in neural networks in general, but still we use them. So it might not be that big of a problem, depending on your situation. Yes?
So you had a slide where you compared the causal models with probabilistic models. So I was wondering, this sounds very familiar, like similar to Bayesian inference, which is applied to...
This one?
Yes.
Okay, yeah.
Which is applied to probabilistic models. So is this causal inference is an analysis tool which can be applied to probabilistic models, or is it something different?
You can say that it's kind of one level up. For every structural causal model that you have, you will get a probabilistic model. Okay. So you kind of, this is one abstraction step more. They live kind of in a parallel. It's not an either or. And I can also say that there are attempts to make like a Bayesian formulation of this framework, and I think there is an equivalence there. But it's current studies, so we don't really know.
Hi, thank you for an excellent talk.
Thank you.
So you mentioned the do-I framework developed by Microsoft. Yeah. Are there any other potentially promising frameworks in the Python ecosystem?
There is a bunch. I have not done the full survey, but there should be at least 3, 4, 5 something. But they have quite different maturity. So this is the one I picked because it's like backed by someone that will finance it, so it will run for longer. Other simpler ones are typically by someone who's done research on the field, or just a, what you call eldsjäl, someone who's passionate about it. So there are definitely alternatives, but I cannot top of mind tell them.
question.
Hi.
Hello.
Thanks for a good talk as well. I was thinking. I was also wondering about this, like, building the graphs and understanding and including everything. And you kind of pointed to causal discovery as the kind of the future. But what about from the previous question? You kind of talked about, okay, if you have a lot of variables, you can start trying to build this graph and understanding what points where. But what if you don't have all the variables? What if you're actually, I mean, because sometimes it's hard, or quite often it's hard, and maybe you're missing something that you can't measure, or you actually don't know, even if you have good domain knowledge, you're missing something. How, is there still strength in this? And I think there must be a problem in research, and like that's kind of what you're trying to figure out.
Yes, it's called the problem with unmeasured confounding.
Yeah.
So there is active research on it. There's like a very ongoing debate. Some researchers has proposed that if you have a lot of variables measured, such as in genetics, for example, where you have like hundreds of thousands, you want sometimes, under certain assumptions, you can actually reconstruct the unmeasured confounding. But then you need other domain-specific assumptions to make it work. You also have complementary toolkits, such as instrumental variable regression, for example, which can be formulated in this framework. So there's no easy answer. There are different specific tools to deal with specific situations, but there is no general answer.
Thank you for all your questions, and you can talk to him in the lunch. And that will be all. And thank you, Ludvig, for coming here and presenting in front of all the really good Python enthusiasts. And this is from us.
Thank you.
Yeah.